just a kind of a quick background on Made in Space. We're a company we're about a 5-year-old company, kind of transitioning out of the startup into kind of small aerospace company regime. And we were founded by basically a bunch of sci-fi geeks, a bunch of guys that grew up watching Star Trek and Star Wars and reading Robert Heinlein, and really into space and saying, why aren't we colonizing space? Why aren't we living and working off the face of the planet? And like a bunch of kind of young guys said, well, we're going to go try to make that happen. And that's really the goal of the company, is to help people live and work in space, to kind of break the paradigm of how we've always gone to space, which is sort of this kind of camping trip model, that we load everything up in you're in your rocket and you blast off to space and you go and do stuff, and then you pack all that stuff back in your rocket and you come back home. You might go there for a few days, you might go there for a few weeks, you might go there for a whole year, but there aren't really people sort of as a going concern really living and working in space yet. So one of the things that it's actually a really good kind of lead-in is sort of the manufacturing problem. That one of the things that existed in every single frontier were tools to manufacture your living space, your living spaces, your other tools, but we don't really have those for space. We don't have this sort of proverbial axe or wheelbarrow of space. And so as a company, we kind of looked at this and said, well, how would we approach this? And very quickly kind of came upon 3D printing as this sort of really sort of fundamental, almost meta tool, a tool that makes other tools for space. And a lot of the reasons that we focused on 3D printing have to do with launch logistics, have to do with how we get everything to space. The way that we've gotten every single thing we've ever put into space to space is loading it on top of one of these guys, loading it on top of a rocket and sending it to space. And these guys are really, really expensive. They cost $20,000 a kilogram or more to get stuff to space. So if you're looking at a cost like that, like a cost basis like that, you don't want to throw anything away. Your sort of traditional like mill and lathe or the sort of proverbial Michelangelo carving away all the marble to get to David doesn't really work in space. You want to create David digitally and have him appear rather than rather than wasting a whole bunch of material that you brought with you. So that's how we kind of said, okay, well, we're going to develop initially additive manufacturing technologies for space. To talk a little bit more about launch logistics, everything that goes to space has to go on the top of these rockets, and it has to get smashed down into a launch fairing, basically. That is a finite volume, and you have a finite amount of mass that you can get to space, which means that if you want to make something that's bigger than maybe 10 meters across, or depending on your rocket, you're going to have to take everything and sort of origami style fold it up and smash it inside that launch fairing, which is all well and good, and we can be really clever in doing that, but it creates all these sort of points of failure, and that's sort of the engineer's enemy in space is our single points of failure. So additive manufacturing as sort of a preview allows me to send just raw material, right, just feedstock in one of these launch fairings, and it can fill up a significant amount of space, right? It can fill up every little nook and cranny with feedstock, and also feedstock doesn't care how many G's I subject it to. A rocket's gonna typically subject its payload to 5 to 10 G's as it goes up, and then it's gonna get to space and it's gonna like float around in zero gravity. So you end up engineering all your everything that goes to space for that sort of first 10 minutes of its operational life, which seems kind of wasteful. But if you manufacture in space, you can sort of avoid that constraint. So you don't have to make things for that that high G environment. So there are kind of 3 paradigm shifts for living and working in space that we in Made in Space are working on today. Those are additive manufacturing in microgravity. That's doing in-space assembly and deployment of satellites, and then there's the kind of big daddy, actual in-space manufacturing and assembly of spacecraft structures and ultimately spacecraft. So about 2 years ago, Made in Space had a lot of press because we deployed with our partners at NASA. We had this great teaming relationship with them for several years, and it's an ongoing relationship now, which culminated in building this right here. This is the very first 3D printer that works off the face of the planet. It turns out there's a lot of things that you have to modify in order to be able to digitally manufacture in space. A lot of engineering and inventiveness that go into that. And so we deployed this printer to the International Space Station about 15 months ago, and began our sort of first printing. And this is kind of a picture of all the pieces that we printed in the first run with this technology demonstrator. This is kind of a busy slide, but it's really just, there are kind of a couple of cool things here to show. So the first part that we made that's down there in the bottom left was actually a printer faceplate. It's actually a piece of the device itself to really, to demonstrate, in orbit, the sort of self-repairing qualities of 3D printers. And then, like any sort of good engineering and science organization, we went through a series of kind of material characterization pieces to say, okay, is this device actually performing how we thought it would? Because we developed this on the sort of the vomit comets that they filmed Apollo 13 in, and astronauts get trained in so they can deal with microgravity. We tested it there, but once it gets to space, maybe things behave differently. And so we tested out a lot of, starting from very simple to more complex pieces. And where we ended up at the end of their very first run was actually, manufacturing complex objects, tools, via this device, and doing it by remotely uploading, remotely uploading the designs. And a really kind of cool demonstration of how, not only why 3D printing is important for remote locations like the International Space Station, but in a way that that 3D printing in particular can help with kind of mission assurance. In space, we made this little ratchet here, and the ratchet has a really cool story behind it. So. This is Commander Butch Wilmore. He was the ISS commander when we, about 15 months ago when we were first printing on station. And he was responsible for taking a lot of the parts out of the machine. And one of those parts was like a little socket head. And he looks at it and he kind of laughs and he says, oh, I'd really like to try this out, but I actually have lost my torque wrench. Because, the ISS is about the size of a house. There's like 6 people living in it. And like you often lose things in your own home where you have gravity to hold them down, the astronauts lose things on occasion. Like things will float off and they'll find them a couple of weeks later, and he lost his torque wrench. And so we heard this and we're like, this is a really awesome opportunity. So we designed up a part that we designed up a working single print torque wrench in a day or so. And then took that through the safety and qualification processes that NASA has for objects to be deployed on the International Space Station, and that took a couple of days. And then we scheduled and NASA scheduled some time for Butch to come and take the part out of the machine. That actually took the longest time because astronauts are really busy folks. And then finally we uploaded the file, and within 3.5 hours of uploading that file, this picture was taken. Butch was very happy that now he has a torque wrench that he can try things out with. But the more crucial piece here is that now we have the ability to, if things sort of go awry or something's lost or we don't have our optimal tool in this remote location, we can fix that. We can with 3D printing. So, and this was all with our sort of technology demonstrator, which is very much the sort of beating heart and brain of a zero-G capable 3D printer. So where we're going from there is in about a month, we are launching this device right here, which is a much more full-featured, really, kind of, alpha, if you will, 3D printer for space. We call it the AMF, or Additive Manufacturing Facility. We spent a lot of money on naming that, by the way. And it's a multi-material printer. It's modular and upgradable, and importantly, it's operated by Made in Space. And so that means that anybody, if you're a corporation, if you're an aerospace company, if you're a non-traditional user of aerospace, if you're a university, if you're an individual, you can come and now have, send stuff to space without putting it on a rocket. And we think that's a pretty amazing opportunity. It prints in, the sort of traditional ABS that MakerBots print in high density polyethylene, as well as aerospace-grade polymer composites like polyether polycarbonate. And it can also be upgraded to metals and some other materials like that. So one of the first things one of the first kind of services, besides just printing on station that we're getting into around doing manufacturing in space, is actually building and deploying satellites. So, and the way that we're doing this is, you have an on-orbit manufacturing capability that can, manufacture in space-proven materials. That's our PEIPC. You can actually, and then you store modular components on station, like electronics boards and things. You can remotely upload software, and then you have an on-orbit ability to assemble and deploy. On the International Space Station, we call this program Stash and Deploy. And it's actually targeted at building like CubeSats, which are these really small, really powerful satellites that are, they're about they start off about this big. You go up to, maybe 3U is their traditional size, maybe about a foot long, and 2 or 3 inches tall. And on the International Space Station, what we'll be doing is storing those modular components, those electronics boards, solar panels, batteries, and then additively manufacturing the structure that holds all those things together and positions them correctly, uploading that software, and then having ISS crew members assemble and then ultimately deploy these things from station. So why is this cool? Besides being really science fiction, it lets us really launch faster. Right today, if you came to me and said, Andrew, here's a CubeSat, put it in space. It'd take me probably 6 months or a year to get a launch, to get it qualified to fly, to wait around for that rocket to go off before you can get it to space. By having these things already, stationed in space, we can cut that time down significantly. We can also avoid a lot of the testing costs that are required for making sure that the satellite works and will survive the launch environment. So the kind of new thing that we're recently starting to talk about is using additive manufacturing to manufacture, larger structures. The two things in here, we have some lovely trusses, that you might use to build, next generation space stations. You also have things like this on the bottom, which is a type of radar that requires 2 things to be separated by vast distances. And these are things that we can enable with additive manufacturing in space. And again, why do we care about this? Well, again, we can reduce that time and cost of deployment. Importantly, we can build bigger, tailored structures that are tailored for their environment. They're not designed to survive a rocket launch and to fit inside a fairing. They're designed to do their mission in a microgravity environment, which means that we can, maybe even make structures that are, sort of impossibly large, according to, to make via sort of traditional deployable technologies. The other thing that's really, really cool here is the ability to, because you have a manufacturing facility right there with you in space, you can actually, during your mission, reconfigure and adapt your satellite. So if you're a commercial satellite provider and your satellite, is designed to cover America, but then, like things often happen, maybe 5 years into its operational life, you decide that Japan is a much more interesting market, or Brazil is a much more interesting market. You can reconfigure that, reconfigure your satellite and point it at, Brazil instead of the United States, and get, have the same bandwidth, but be, adapted for that. And that's something that we really sort of take advantage of. We take for granted, rather, on the ground, like the ability to take something apart and, add to it. And that doesn't exist in space currently. So there are really kind of 4 key pieces to doing in-space manufacturing and assembly, in our opinion. The first piece is being able to actually do additive manufacturing in a microgravity environment. And that's something that we demonstrated about 15 months ago. The next piece is you need to be actually able to do that with vacuum-rated materials in a vacuum. It turns out that a lot of materials, if you put them in a vacuum, ABS, for example, basically just fall apart. And so that's not really appropriate for building a spacecraft out of. The next piece is being able to manufacture extended complex structures. If we go out in the hall today, there are a lot of 3D printers, and they're like this big, and they make things that are smaller than they are. And that's really that's completely appropriate for what they're doing. But we're unlikely to launch a 3D printer to space that's like 100 meters long to chunk out 50-meter objects. We're gonna want to use something that is small but can actually create those complex digital structures that we all know and love from that small form factor. And so we've actually developed some technologies at Made in Space that that enable that. And the fourth key piece is the ability to assemble, and that requires in-space robotics. And there are luckily a lot of companies that are really good at it, right? The shuttle's had this lovely robotic arm. Station has a couple of really amazing robotic manipulators on it, and those are made by companies that are really good at their jobs. And those are sort of those four key pieces, which also ultimately enable us to build assets in space rather than on the ground, and giving us new capabilities and making things that are a lot more resilient. So for those of us that like pictures, here are kind of a couple of example mission profiles. So, and they kind of start from like simple to more complex. At the most basic level, you have just manufacturing like booms, so that I can put a sensor or something out on the end of it that's optimized for my environment. If we go one step up from that, we have hybrid in-space manufacturing. You can make those booms, and you can, as you're manufacturing, you're implanting your sort of functional components and your wiring harness, and then you're attaching maybe solar panels or something like that on the end. This next one, the future space stations, which is up here on your right. This is actually a really important one. The International Space Station is this amazing asset that orbits our Earth, every 90 minutes, and 6 people, live and work on it. But it's currently slated to be decommissioned in less than a decade. It's a $150 billion asset that we're gonna, that right now the plan is to get rid of in less than 10 years. And there are lots of companies. There's lots of amazing research and science and soon manufacturing that occur and will be occurring on that asset. And there'll also be people that want to go to it. People have gone to it as tourists in the past, but we're planning to dump it in the ocean in a decade. So there's this anticipated need for a continuing presence there. And the International Space Station was built with shuttle. It was built over like 40 missions, which is a lot. But we don't actually have the benefit of shuttle anymore. We don't have the benefit of putting astronauts in EVA, spacesuits, and having them go put things together. So we're going to need the ability to actually assemble these stations in the future robotically, and that's where this technology is really I think an area that it will really shine. Another area that's kind of a little further down the line that we're really excited about though is something I call sort of the high density satellite. Is you really design from the ground up a satellite a satellite bus that fills up that entire launch fairing. It's got all of its prefab components and feedstock in it, and then once it gets on orbit, it just manufactures the entire satellite to something that's significantly larger than you might be comfortable smashing inside that fairing. So, just to kind of recap, there are kind of three areas that we're really pushing that additive manufacturing is enabling in space. That's responsive remote manufacturing on the International Space Station. It's deploying space assets like CubeSats in a very fast way with our in-space assembly and deployment of satellites. And finally, that in-space manufacturing and assembly, which is going to let us create optimized, never before achievable spacecraft than we've ever seen in space. So thank you guys very much.